This program is sponsored by Varus Research, at the forefront of the latest scientific research and technological developments through engineering.
Varus Research, where advanced technologies, cutting-edge scientific research, and intelligent innovation meet to transform complex theory into real-world solutions. Online at varusresearch.net.
Interactive Science Programs presents educator Dr. Darryl Baynes.
Hi, I'm Dr. Darryl Baynes, President and founder of Interactive Science Programs. We're one of the largest science and math outreach companies in the nation, owned and operated by African Americans. We all learn science through our everyday experience, so we're going to do some science today. We're going to talk about whether something is hot or cold. Pretty simple, whether something is hot or cold. Okay? And we're going to use everyday things to talk about it. So for example, here's a tea kettle. If the liquid in the tea kettle is boiling, then the whistle goes off. If this tea kettle is sitting on your stove at your house and the whistle goes off, the liquid inside will be hot. So I'm going to pour some liquid in here. Notice our liquid is boiling. So now the question is whether the liquid I poured in here is hot or cold. We know that if this tea kettle were sitting on your stove in your house and the whistle goes off, that the liquid would surely be hot. But if we look real close at this, we see frost on the top of this tea kettle, which gives us an idea that the liquid inside is really cold instead of hot. The liquid that I put in there is a liquid called liquid nitrogen. And as we have our liquid in our container and it's boiling, I can then open the top and all of our liquid has evaporated away. So what I put in there was liquid nitrogen. So first let me show you what I carry my liquid nitrogen in. This thing is called a Dewar flask. And nitrogen is part of our periodic table, and it's an element on the periodic table. And nitrogen itself, as an element, is up at the top row. So let me introduce you to the periodic table of elements.
And now, ASAP Science presents the elements of the periodic table.
There's hydrogen and helium, then lithium, beryllium, boron, carbon everywhere, nitrogen all through the air with oxygen so you can breathe, and fluorine for your pretty teeth, neon to light up the signs, sodium for salty times,
Magnesium,
aluminium, silicon,
phosphorus,
then sulfur, chlorine, then argon,
potassium,
and calcium so you'll grow strong,
scandium,
titanium, vanadium, and chromium, and manganese. This is the periodic table, noble gas is stable, halogens and alkali react aggressively. Each period will see new outer shells where electrons are added, moving to the right. Iron is the 26th, then cobalt, nickel coins you get, copper, zinc, and gallium, germanium, and arsenic, selenium, and bromine film, while krypton helps light up your room, rubidium, and strontium, then yttrium, zirconium,
niobium,
molybdenum, technetium,
ruthenium,
rhodium, palladium,
silverware,
then cadmium and indium,
tin cans,
antimony, then tellurium, and iodine, and xenon, and then cesium, and barium is 56, and this is where the table splits, where lanthanides have just begun, lanthanum, cerium, and praseodymium. Neodymium's next to promethium, then 62, samarium, europium, gadolinium, and terbium, dysprosium, holmium, erbium, thulium, ytterbium, lutetium. Half hafnium, tantalum, tungsten, then we're on to rhenium, osmium, and iridium, platinum, gold to make you rich till you grow old, mercury to tell you when it's really cold, thallium, and lead and bismuth for your tummy, polonium, astatine would not be yummy, radon, francium will last a little time, radium, then actinize at 89. This is the periodic table, noble gases stable, halogens and alkali react aggressively. Each period will see new outer shells will electrons are to the right. Actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, isonium, fermium, indolium, nobelium, lawrencium, rutherfordium, wm, sprigium, borium, hesium, meitnerium, dubsidium, mercenium, copernicium, nihonium, flerovium, moscovium, livermorium, tennessine, and organesson, and then we're done.
We don't, in our everyday life, go through and interact with each one of the elements on the periodic table, but our bodies are made up of these elements. The number one element that our body is made up of is oxygen. 65% of our body is made of oxygen, 18% is made of carbon, 10% is made of hydrogen, and then 3% nitrogen, and then 4% other elements and other stuff in our bodies. Now, some of you have one of these at home, and it's called a thermos bottle. Duraflask thermos bottle, they're exactly the same thing. I also have done contract work at the Kennedy Space Center where the space shuttle takes off. The large external fuel tank, the orange fuel tank for the space shuttle, was nothing but a giant thermos bottle. It would hold 555,000 gallons of rocket fuel. So I put a picture here so you could see people standing at the base of the space shuttle to get an idea of how tall it was. Now you may look at this and think that's the biggest thermos bottle I've ever seen, but actually, these are the biggest. This is the liquefied natural gas cargo ship. I used to live in West Virginia where they do something called fracking. They take gas out of the ground, they make it so cold it turns into a liquid. They put the liquid into these giant thermos bottles on these ships, and as the ship goes across the ocean, a little bit of the liquid turns to a gas, comes down the pipes and runs the engines. These ships need no external fuel at all to operate. They operate on the liquid that they're carrying. In here, in our thermos bottle, Duraflask, we have liquid nitrogen. Now, I want to give you an idea of how cold this stuff is. So we have our temperature chart here. This temperature chart, we have degrees C on one side, and we have degrees F on the other side. C is for Celsius, F is for Fahrenheit. We use Celsius in science because it just makes more sense. In the Celsius scale, water boils at 100 degrees, water freezes at 0. On the Celsius scale, liquid nitrogen is 196 degrees below 0. So we're going to pour some out. Let me put on my safety glasses. And this is also a Duraflask thermos bottle. See, I keep my juice in there. All right. So in our Duraflask, we have liquid nitrogen. Right now it's boiling vigorously because our Duraflask was warm. I just poured it in there. So suppose it's raining outside. The ground is wet. When it stops raining and the sun comes up, the water on the ground evaporates away. Evaporation is when a liquid turns to a gas. I'm going to pour a little bit of this liquid nitrogen out on the floor, and you will see it turn to a gas. The floor is warm, the liquid is cold. As soon as the liquid touches the floor, it immediately evaporates away and turns into a gas. So we have our liquid nitrogen in our container. We're going to do an experiment. I have a balloon here. I'm going to fill this balloon up with my air. I want you to notice I'm using a clear balloon so you can see through it. My air does not have a color. So in this balloon is my air. Okay. When we breathe, we've all been taught that we exhale carbon dioxide. So frozen carbon dioxide is a white solid called dry ice that we buy from the store. If we exhale carbon dioxide and we freeze it, we should see dry ice on the inside of this balloon. Okay. So we're going to take this balloon and put it in liquid nitrogen. But I want you to think about this. I wonder how many of you out there have ever seen the movie Terminator 2. This is my favorite scene in the movie. The Terminator 2 crashes in a tanker truck of liquid nitrogen. While he's walking through the liquid nitrogen, he begins to freeze. We're going to take this balloon and put it in liquid nitrogen. The balloon could freeze solid like the Terminator. The balloon could get bigger, could get smaller, or it could pop. So I have my spoon ready. First thing I'm going to do is pour some liquid nitrogen into our bowl. Take our balloon. So I'm pushing the balloon down into the liquid. Notice our balloon is getting smaller. The air in the balloon is curling up, trying to keep its heat, so the whole balloon is getting smaller. This gives us an idea that as things get cold, they contract, they get closer together. So notice it looks like a Hershey's Kiss. I'm going to keep pushing down with my spoon so we don't get our hands in it. Okay. I'm going to grab the balloon by the edge and lift it up. When I do, you will not see just dry ice on the bottom of this balloon. What you will see is a white liquid. It is incorrect to tell students we exhale CO2. That's wrong. The air we breathe is 78% nitrogen, 21% oxygen. So when you breathe in, that's what you breathe in. When you breathe out, you exhale 78% nitrogen, 16% oxygen, and 5% carbon dioxide. So most of what you exhale is nitrogen and oxygen. They don't tell you about it because it doesn't do anything. You only exhale a little bit of CO2. If we do the experiment right, we'll be able to see it. So the first thing I'm going to do is lift it up. You'll see the white liquid. Then we're going to blow this balloon back up from the outside. So that white liquid right there, that's my air. Now watch what happens. You see a little bit of white stuff? That's a little bit of CO2 we exhale, which is a solid that turns into a gas. That's called sublimation. Balloon is still tied off. It's the same air that was in there before. As things get cold, they get closer together. As they warm up, they get farther apart. The little bit of CO2 was a solid. As it warmed up, it turned into a gas. It's called sublimation, when a solid turns into a gas. It is a physical change. Okay. Solid molecules are very close together. Liquid molecules are a little farther apart. Gas molecules are very far apart. We had a gas, we turned it into a liquid. We warmed it back up, it turned right back into a gas again. The difference between a solid, liquid, and a gas is how far apart the molecules are. You will see this again when you take physics in high school. This is called entropy. Randomness of the system is entropy. In general, as things get cold, they get closer together. As they warm up, they get farther apart. Now, I still have liquid nitrogen left in the bowl, but I'm not going to pour it out. There's a liquid forming on the bottom of the bowl. And since our table is white, it's hard to see. So I'm going to put my glove. You can see it hitting the top of the glove, turning into a gas. So there's a liquid forming on the bottom of the bowl. It is not liquid nitrogen. What's forming on the bottom of this bowl is pure liquid oxygen. The bowl is so cold at 196 degrees below zero, it's condensing the 21% oxygen right out of the air. As the bowl gets cold, the liquid oxygen rolls down the side of the bowl, condenses into a drip, into a liquid, and then falls off. As soon as it hits the glove is warm, it turns right back into a gas. You can see the little puffs coming off of it. So that's pure liquid oxygen. Okay. Now, in general, as things get cold, they get closer together. As they warm up, they get farther apart. But there's an exception to the rule. There's one thing, when it gets cold, it gets bigger, and that's water. So you think about it, when you pour water into an ice cube tray, the ice cubes are bigger than the amount of water you put in. When water turns to ice, it expands. The reason it expands is because water has a plus side and a minus side. It is a dipolar molecule. When the pluses and the minuses meet up, it makes a crystal structure with holes in it. That's why ice floats. That's why ice floats in your soda and in your water. That's why ice floats in the ocean, because ice is less dense than water. That's also where the saying comes from, tip of the iceberg. Because when you see ice floats, the majority of the ice is underneath the water. You only see a little bit above the water. All righty, now, when water turns to ice, it expands with a force of almost 31,000 pounds per square inch. So if you take a soda, you put it in the freezer, the molecules are going to freeze and expand, and it's going to explode the can, because the can can't hold 31,000 pounds per square inch. So now let's apply that. I wonder where potholes come from in the street.
Potholes are formed by water flowing through small cracks in the pavement, then freezing, pushing the pavement up and the subsurface down. Warmer weather thaws the ice, creating a cavity which caves in when cars drive over it.
And as we think about this, our bodies are mostly made of water. So what happens when the water freezes in your body?
The human body is about 60% water. And when water changes from a liquid into ice, the molecules stop moving around freely and lock together to form crystals. And that destroys cells.
So let's try another experiment. We saw what would happen when we put our balloon in liquid nitrogen. Since our bodies are mostly made of water, if our fingertips, for example, get too cold, we get severe frostbite. And frostbite is when the molecules of water freeze in your cells and swells up and breaks the cells apart. That's frostbite. Those cells are dead. They'll get replaced. Okay. If they don't get replaced, then the digit turns black and you have to get it cut off. One of the things that can be done now for cartilage areas, your nose, your ears, if they get frostbitten and they have to cut them off, they can take cells from another part of your body and on a 3D printer, digitally print you a new nose or ear and put it on, and it'll look exactly the same. Okay. So now we put our balloon in. Let's try a ball. So we're going to compare my balloon and the ball. So my balloon is almost round, my ball is round. If I squeeze the balloon, the air doesn't come out. If I squeeze the ball, the air doesn't come out. I can bounce my balloon. Okay. I can bounce my ball. we're going to put this ball in liquid nitrogen. We want to think if the ball will shrink like the balloon did. So let's see what happens. We have our Dewar flask here with our liquid nitrogen. Have my safety glasses on. When I put this balloon in liquid nitrogen, the ball in liquid nitrogen, it's going to float. I'm going to hold the ball down under the liquid nitrogen with my spoon. Put on my gloves. Drop my ball in. I'm holding the ball down under the liquid nitrogen with my spoon. This only takes a few seconds to work. Take the ball out. Notice it's still round. I can squeeze it, bounce it. So this is what happened. The rubber that the ball was made of was thicker than the rubber that the balloon was made of. So the outside of the ball froze solid, but the gas on the inside of the ball still condensed into a liquid just like the balloon did, which left a vacuum. When I threw the ball down hard enough, once I cracked the outside air pressure rushed in to fill the space that was emptied because the gas turned into a liquid. So that pop you heard was an implosion. The ball exploded towards the inside, implosion. When the ball exploded, there is 1 atmosphere of pressure all around us pushing down on that ball, okay? Now another place this air pressure thing is important is rocketry and aviation. I'm also a pilot. Or we think about the space shuttle. 1986, Space Shuttle Challenger was sitting on the launch pad. As it was sitting there, in between the solid fuel boosters and the liquid fuel tank were these things called rubber O-rings. As it was sitting on the launch pad the night before the launch, the temperature went below freezing. So the whole space shuttle, including the rubber O-rings, were frozen. The next morning, when the space shuttle took off, the rubber O-rings were still frozen. As the space shuttle was going up, they tell the commander, go with throttle up, push the engines as hard as you could. When they try to, instead of the rubber being able to stretch, it cracks.
Engines throttling up, 3 engines now at 104%.
Challenger, go with throttle up.
Challenger, go with throttle up. 1 minute 15 seconds. Velocity 2,900 feet per second. Altitude 9 nautical miles. Downrange distance 7 nautical miles.
And the space shuttle blows up. So the space shuttle blows up because rubber doesn't stretch in the cold, essentially. And unfortunately, these are the astronauts that were on the Challenger January 28th, 1986. Okay. So we see what happens with things in rubber and liquid nitrogen. Let's try something made of metal. So we still have liquid nitrogen left in our Dewar flask. And this is called a bimetal strip. It is shiny on one side, dull on the other. The dull side is brass, the shiny side is silver. So I'm going to put it in liquid nitrogen. And then when I take it out, notice it's bent over towards the darker side. When the brass metal gets cold, the molecules get closer together faster than the silver on the back, so it bends over in this direction. I'm gonna wave it around and warm it up. What should happen to the metal? It should straighten back out because as things warm up, they get farther apart. So notice, as I'm doing this, it's getting straighter. All of you have one of these in your house. It's attached to the wall, used mostly in the winter. It's called a thermostat. You take the cover off your thermostat, you'll see a long coil wire. When the house gets cold, the wire gets smaller, makes a metal connection, turns your furnace on. When the house gets warmer, the wire gets bigger, breaks connection, turns your furnace off. So the whole time while you're at school or work, the little wires opening and closing, turning your furnace off and on. Okay. Now this is a thin piece of metal. So let's see what happens with a thicker piece of metal. So I have a thick piece of metal. This metal's a lot thicker than this one, if you compare the two. We're going to put this in liquid nitrogen to see if it will change shape. First thing we have to do is put the ball through the ring. That'll tell us how big the ring is. So I'm put the ball through the ring. So you notice the ball goes through the ring. I'm going to hold the ball in my hand, and the ring I'm going to put in liquid nitrogen. As soon as I put the ring in liquid nitrogen, the liquid began to boil. The liquid's boiling because the ring is warm at room temperature, and the liquid is cold, so the ring is making the liquid boil. When the liquid stops boiling, the ring should be the same temperature as the liquid, negative 196 degrees below 0 Celsius. So it's still boiling. And it just stopped. I take it out, take my ball, push it through. Notice it won't go through. The ball was in my hand is warm, the ball got a little bit bigger. The ring was in liquid nitrogen, the liquid was cold, the ring got a little bit smaller. Now I have a problem because I broke the thing, it won't work anymore. So what can I do? I can put the ball in the liquid nitrogen and make the ball smaller, and that may work, or I could warm the ring up. One of the warmest things we have is our hand, but if I grab this with my hand, it's so warm, this is so cold, it'll burn a hole in my hand. So I have to rub it real quick. And I'm using frictional heat to warm this up. Ooh, is that cold? Okay, so I warmed it up. I take my ball, and the ball goes right through. So even thick metal will change shape in a cold environment. I grew up in Philadelphia. In the wintertime, stop signs, stop poles, they get a little bit smaller because it gets so cold. In the summer, they get bigger because it gets so hot. Okay. This also happens, it used to happen with the space shuttle, but it's happening right now, this very second, on the space station. As it orbits the Earth, when it is facing the sun, it is 200 degrees above 0 Fahrenheit, the space station gets bigger. When it orbits away, approximately 200 degrees below 0 Fahrenheit, the space station gets smaller. So the whole time as it orbits, it expands and contracts. When you're inside, you could hear the thing creaking the whole time. This is the same sound you hear in your house at night, especially if you live in the north. In the winter, you're trying to go to sleep. The house is quiet. The furnace comes on. As the warm air goes through the ductwork, you hear the house starting to creak and expand. Same thing. This is also how they make airplane wings. They drill holes in the metal, and then the rivets are too big for the holes. They shrink the rivets in liquid nitrogen, pop it in the hole. The rivet will warm up in the hole, and it'll swell in the hole, and it'll never come apart. So you never hear about an airplane vibrating or anything like that in flight, because all of the rivets are cold riveted together. It won't come apart. When it goes up in the sky where the temperature's cold, the metal shrinks a little bit, the wing, and the rivets shrink at the same rate because they're both made of the same metal, called cold riveting. And the opposite is true for anything metal. For example, the Eiffel Tower gets 7 inches taller in the summer as a result of the expansion of the metal in the heat. So in general, as things get cold, they get closer together. As they warm up, they get farther apart. So let's look at this. I'm going to take a little paper towel, fold it over, and fold it over again. Right now, our paper towel is dry. I'm going to crunch it. Notice nothing much happens. I'm going to put it in liquid nitrogen. I'm going to count to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I take it out of the liquid nitrogen. You can see where it was in the liquid. I'm going to crunch it again. Notice smoke comes off, but nothing much happens to it. I have a bucket of water here. I'm gonna wet it. Okay. Put it in my liquid nitrogen again. You can hear it boiling. Count to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Take it out. When the paper towel was dry, nothing happened. As soon as you made the paper towel wet, it could crumble and fall apart. Okay? And again, this brings us back to the human body. What happens if we put the human body in liquid nitrogen? So we saw what would happen to the Terminator. He froze. If we think about Star Wars, we saw what happened to Han Solo when he was frozen in carbonite. Now, we can't freeze people in carbonite, but there is a company in Scottsdale, Arizona. Let's say you're dying from a disease they can't cure, like stupidity. They will freeze you in liquid nitrogen with the idea that when they come up with a cure, they'll thaw you, fix you, bring you back to life. But we know that the cells will rupture. But there's this new stuff that they have. This stuff is called M22. And this is a little bit of information about it.
The antifreeze is the key. It's called M22, a strange substance that's not toxic to rabbits or humans.
And as you can see, at room temperature, it's clearly a liquid.
I imagine M22 must, of course, work better than M20 and M21 did.
Well, M22 is named because it's intended to be used at minus 22 degrees Celsius, which is minus 8 degrees Fahrenheit.
And when they take it down below those temperatures, it behaves strangely.
Cooled to below minus 100 degrees Fahrenheit.
Whoa!
And it's now like a viscous syrup.
Pump this into a kidney, and no matter how cold the organ gets, it won't freeze. How does that work? Unlike solid ice, where molecules are tightly organized, Fahey's cryoprotectant remains liquid no matter how cold it gets.
At a certain point, there's insufficient heat energy in the system to maintain molecular motions, and the system just locks up as a solid, but it's not a frozen solid. We're going to a very different kind of solid state.
So it's a solid, but it's not ice.
It's called a glassy solid state, sort of like a window pane.
So it's not called freezing organs, you're
vitrifying those organs.
Vitrifying.
Now, at this company, let's say if you're dying from old age, they will cut off your head and just freeze the head with the idea that years down the line, they'll be able to make a robotic body or build you a new body and put your head on it, much like on Futurama. For the whole body, it is $220,000. For the head alone, it's $80,000. They don't know how to thaw you out yet, but they're thinking technology will get better, and eventually they'll figure it out. Okay? We still have liquid nitrogen left in our Dewar flask, and anytime something warm gets near it, a little bit of a cloud comes out. Okay? Now, a cloud close to the ground is something we call fog. The definition of fog is a cloud within 50 feet of the ground. But it makes me wonder exactly what is a cloud. So, I'm going to take our bucket of water and I'm going to make a cloud in this bucket of water. And we only have a little bit of water about down here. I'm going to pour liquid nitrogen in. Water represents the warm, the liquid nitrogen represents the cold. Where the two meet, we'll get a cloud. This is a cloud. You can feel it. I can put my head in it. that's smooth. So now, as we think about this, we're up close on a cloud. A cloud is either a liquid, a gas, or both. And most people tend to think that a cloud is both a liquid and a gas, but actually a cloud is an example of condensation, when gas turns into a liquid. Therefore, a cloud is a liquid. The average cloud weighs between 2 and 3 tons, is the weight of the average cloud. And you can tell a cloud is a liquid because rain comes from the cloud. A cloud close to the ground is fog. When you're driving in a car through fog, you got to put your windshield wipers on. You're driving through a mass of liquid, 2 to 3 tons. Okay. Now let's see if our camera can see what the cloud looks like in front of it. And if you listen close, you can hear the water in the bucket freezing and crackling. Alrighty. Now, sometimes when I do experiments, they take a while to work. And this one takes a few minutes. So I want to get it started. And all I have to do is pour a little bit of liquid nitrogen into this flask. Yep, just a little bit. Okay. And we have to let this sit for a minute, so I want to get it started so we don't run out of time. Now what? Wait a minute. So what? Maybe I'm not putting the top on hard enough. So every time I put the top on, the top pops off and all of the liquid nitrogen is gone. This is what's going on. When I poured the liquid nitrogen in, our glass was warm. The glass made the liquid evaporate away and turn into a gas. As the pressure builds up, it pushes the top out. Okay. So what happens if we pour liquid nitrogen in here? They are both the same size. The rubber stoppers don't make a difference. I put these pieces of ribbon on here so that if I shoot it at somebody, they can see it coming and won't get knocked upside the head. Other than that, they're the same. Except this one has a sidearm. So we're going to pour liquid nitrogen in. Notice I poured a little bit more in. Put the top on. Our liquid is boiling, coming out the hole in the side so the top won't pop. What happens if I cover the hole? The top should pop off, so let's cover the hole. Now, I didn't say what I was going to cover the hole with. As the pressure built up, it filled up the balloon until the balloon popped. So, where does this take us? Well, let's think about our Dewar flask. Every time I take the top off, the top is loose. There are no threads on here, nothing to keep this on tight. This top is loose, it's always loose. It has to stay loose because if it doesn't, this whole tank will blow up. If you see a tanker truck driving down the street and it says refrigerated nitrogen on it, it's liquid nitrogen, and it has to have a vent at the top so the little bit of the liquid nitrogen can turn into a gas so the tank doesn't blow up. Same thing. If I come to your school, then we're going to set off a nitrogen explosion. I can't do that here, but That's what we do at schools. This is science going on around us every day. And all we're talking about is, starting with, is whether something is hot or cold. That's all it is. Science is a part of everything we do. Every day, we're interacting with science. And if you're interested in science, there are a lot of jobs out there, a lot of opportunity. It's better to be prepared when you have an opportunity than to have an opportunity and not be prepared.
Thank you for watching Interactive Science Program's Science Presentation. Special thanks to the following: Veris Research, at the forefront of the latest scientific research and technological developments through engineering. New Mexico Museum of Natural History and Science. Piedmont Players Theater, thank you for the continued support of the arts. The Blanche and Julian Robertson Foundation.
These my dollars make it hurt.